This is the training module for CDI, which is Coherent Diffraction Imaging. So starting with the technique basics, it makes sense first to do some comparisons to existing microscopy techniques. And I pulled here just some simple pictures from the internet, a profile of a TEM and an optical microscope operating in transmission mode. Basically you have light, or in the case of the TEM, electrons coming from a source, goes through some kind of optics to focus it onto the sample, and then some of the either electrons or light are transmitted, and then they're focused by another objective lens onto some kind of viewer or a camera at the bottom here. And the reason I point this out in particular is that I want to take note of the lens that exists between the sample and the detector or the camera. And this is typically true for microscopes that work both in transmission or reflection geometry. It's a little bit different for something like an SEM, where you're just scanning a probe across a surface, and your resolution in that case is dictated by the size of that probe or that electron spot. But in general, for many techniques, you need to have some kind of lens or focusing optic in there to ultimately produce the image of your sample or your specimen onto the detector. But that kind of leads to the question, what if we have a light source that should, in theory, just by the nature of that light, be really attractive for producing high resolution and high contrast imaging data by the way that it interacts with the sample, but we have a problem because we don't actually have good lenses for that type of light. And that means we're going to have a difficult time focusing that light, and we're going to have a difficult time producing an image because we don't really have an objective lens. So we kind of end up with the challenge here. And so that's where coherent diffraction imaging is one of the solutions to this challenge. And the way it works is in principle quite simple. We shine a coherent light source onto a sample, so we're of course using a laser beam in this case. And we can describe that with a few parameters. We've got some wavelength that those photons are representing, or some frequency, you could say. E in this case just represents the amplitude or the intensity of that light, and phi is the phase, right? So any wave propagating through space is going to have both an amplitude and a phase. And we're going to hit it on the surface of a sample at some angle, theta. So when that happens, we illuminate a spot that's just the size of that laser beam, and some of those photons are going to bounce off the surface, and then we can characterize that reflected beam again by the same wavelengths are going to exist there, but now we're going to have a different amplitude, so E sub r, and a different phase of those waves as well, so now phi sub r compared to the I subscripts for the incident light. And it turns out now when we put a detector here, the image we get isn't actually just a direct image of the sample the way we would intuitively expect to see it, but it's actually some kind of more complicated diffraction pattern that looks like this. And basically what this is showing is it's taking a Fourier transform, or a frequency transform, of all the various features that exist on our sample and putting them into frequency space, and we're detecting kind of this frequency diffraction image. So there's a lot of information in that, but it's, clearly without having the lens here that you would have in a normal microscope, it's not necessarily intuitive what we're looking at there, the way we're sort of classically used to in microscopy. But the way we extend this to a full microscopy technique is we then raster that spot across the sample, and this can be done either by moving the spot or moving the sample. It's kind of equivalent. And we collect many of these diffraction patterns at different spots. And one of the keys with this tychography approach is we actually overlap those spots by a significant margin. So this provides some redundancy of information that's used later on to help us interpret all of these diffraction patterns that we produce. So we go and we march across our entire sample and we collect, it could be up to a few hundred of these spots, something like that, depending on how large of a field of view we need. So that's how we collect data, but what information ultimately does this provide to us? So I repeated that diagram here just to remind you what's actually going on during the data collection, and we get many of these diffraction patterns, as I said, for these different spots on the surface. And then we're going to use a smart computer program that's going to reconstruct all of those diffraction patterns. So this is following a tychography type of approach, And this is an algorithm, essentially a data processing tool that's included as part of the quantum microscope. It's kind of the way you're now going to transform this diffraction information back into the real space, the way we're used to seeing it. And we end up getting things that look like this. You basically get two overlapping data sets or modalities, if you will. One representing the amplitude of that reflected wave, and the other the relative phase shift of that wave as it reflects off the surface. And these are just color-coded for the sake of kind of visualization in this diagram. So what's that actually mean for microscopy? Well, if we kind of take a broad look at it, microscopy really needs two things to be effective. You need sufficient resolution to be able to see whatever small features you're interested in. But of course, resolution doesn't mean anything without some sort of contrasting method to be able to tell one feature from another or one type of material from another. So these two things really go hand in hand. So we need both this resolution resolving capability and a source of contrast. Well, what we get with CDI is we get this amplitude and phase information, and it turns out there's a lot of information about both high resolving power and contrast sort of encoded within these two types of modalities. So basically it's going to give us a mix of compositional information, so different phases of material or different elemental or chemical compositions, and that's primarily manifested in the amplitude information. That will be really sensitive to different material types. But it also gives us topography or height contrast, and that's actually going to come mostly from this phase image that will be very sensitive to topographical variations across the surface. There's a little bit of kind of decoding necessary to go from amplitude and phase, which is what you're given, to composition and height, which is what you're probably really interested in. But the information is there, and it is kind of encoded in these images. And ultimately, this is really dictated from a spatial resolution perspective by the wavelength of the light. And this is where we get a really nice advantage of working with extreme ultraviolet or soft X-ray light, where having the short wavelengths can then directly translate to high imaging resolution. So we're talking here on the couple tens of nanometers type of spatial resolution. And this can be done across fields of view of multiple microns in size, and we can acquire this data in a matter of minutes and then feed it into this reconstruction process. So ultimately, for those of you who are familiar with other microscopy techniques, a nice comparison can be made here that we're taking aspects of SEM in terms of the spatial resolution and to some degree some of the compositional type of information, and AFM, which is really known for its topography height mapping capability, and kind of blending those two together and then adding some additional functionality where we should get chemical sensitivity to low density and different binding states and chemical variations that are probably even better than either of these two. So it's kind of building upon existing techniques and then adding some new stuff. So it should fit nicely into that whole multi-scale, multimodal, correlative imaging idea that's pretty popular in the microscopy world today. So light sources, what's required for CDI? Well, the number one is kind of right in the name, which is the number one requirement of light sources for coherent diffraction imaging is a high level of coherence. And coherence means that basically all the photons are oscillating together in both space and time. So I pulled this diagram from the internet. You can look at light that comes out of sunlight or an incandescent light bulb where you have all kinds of different wavelengths. They're all different phase and sort of mismatched relative to each other, so you'd call this very incoherent. You can also have LED light, which is just a single wavelength, but it's not in phase with each other. So this is also not coherent because it's out of phase. And then you have laser light, which classically is monochromatic and in phase, meaning all of the oscillations here happen together. So that's a very coherent beam, which is what lasers are known for. Of course, in the ultra-fast laser world, we're not actually dealing with perfectly monochromatic light. We've got a bit of a spectrum mixed here together, which is what gives us the ultra-short pulses. But the key is that those are oscillating in a very well-defined phase relationship. So even though we don't have perfectly monochromatic beams, it's still very coherent because of the fact that all that light is in phase and provides a very predictable oscillation and wavefront. So it turns out light that follows this kind of description really only comes from two places as far as experimental sources. One is from synchrotron beamlines, one of the things they're very well known for. And incidentally, also most of the origin of CDI imaging comes from synchrotron developments, not surprisingly. And lab-based coherent laser sources. So again, this is true for both monochromatic and non-monochromatic laser light. And of course, in our case, we're talking about ultra-short, short wavelength laser light, but it is highly coherent, and that's a really important property of this light to be able to do CDI imaging. And why do we care about doing this with KM Labs, or why can we do this better than other people? Well, it turns out to create a CDI microscope is a variety of things that need to come together. You need, of course, the light source. Then you need the imaging station, where you're actually going to have that light interacting with your sample and producing the data that you need. And you need the ability to process that data and finally extract whatever useful information you actually need from it. And KM Labs is really uniquely positioned to bring these ingredients together and create an effective microscope, building principally on our classical strength as the light source providers, but now incorporating additional know-how on the imaging and data processing side as well. And the great thing is we're actually building upon a pretty good wealth of experience here, where our relationships with University of Colorado, the KM research group there, as well as JILA, where they've done some of this type of work in the past. And so we have some proof of concept experiments. We have some knowledge to build upon here, and we're really leaders. There's hardly anyone else in the field doing this type of experiment, mostly because it's just so hard, especially on the light source. The requirements are so stringent that it's not an easy thing to do, but we're really uniquely positioned there. And of course, we can also extend this to dynamic imaging by leveraging the ultra-fast pulses of light that we have, or complementing it with additional modalities that we've seen in some of the other training modules, things like ARPES or pump probe spectroscopy or PEAM or so on, that can also benefit from these types of sources.